Hello everybody, my name is Florian Rademacher. I'm a PhD student at the University of Applied Sciences and Arts in Dortmund. And in the following, I'm going to present our paper with the title A Modeling Method for Systematic Architecture Reconstruction of Microservice-Based Software Systems. So let me directly jump into the introduction. Our approach is concerned with software architecture reconstruction of microservice architecture, or short MSA. MSA is a novel approach towards architecting service-based software systems that puts a strong emphasis on service-specific independence. Specifically, MSA promotes to tailor services to distinct capabilities, shift the responsibility for a service to a single team, and enable the isolated execution, testing, and deployment per microservice. MSA aims to increase architecture scalability, maintainability, and reliability, and is often used to refactor monolithic systems for which such quality attributes decreased critically. However, and this is the problem statement of our paper, when adopting MSA, its trade-offs lead to an increased architectural complexity when compared to monolithic systems. And this architectural complexity leads to an aggravation of software architecture reconstruction, or short SAR, of MSA-based software systems. SAR means the process of recovering information about a software architecture for which no architecture documentation exists or whose architecture documentation is outdated. One goal of SAR is to answer hypotheses about the reconstructed architecture by facilitating architecture analysis. And our contribution is a structured modeling method for SAR of MSA-based software systems that guides the SAR process by aligning its steps to architecture viewpoints that were specifically defined for MSA and that focus on microservice design, development, and deployment. Our modeling method employs a set of viewpoint-based MSA modeling languages that we developed within our previous research, and we aim to facilitate architecture analysis by means of the abstraction introduced by the models. Moreover, we validate our approach by means of a case study architecture and its analysis and the analysis of its risk and technical debt. So our modeling method builds up on the four-phase SAR process defined by Bass et al. In the first phase, the raw view extraction, coherent sets of software architecture information, or short views, are gathered from input artifacts. These input artifacts can be any artifacts that are related to the software architecture to be reconstructed, like, for example, source code, configuration files, build scripts, but also documentation that lies on a higher level of abstraction. Phase 2, database construction, transforms the views into canonical representations and stores them in a structured form. Phase 3, view fusion and manipulation, combines the views to improve accuracy of the reconstructed information. And this combination can, for example, be the identification of relationships between views. Phase 4, architecture analysis, answer hypotheses about the examined architecture, starting from the combined views. And on this slide, you can see our proposed modeling method for SAR of microservice architectures in the form of a UML activity diagram. And the black circles indicate the correspondence of each activity to one or more phases of the SAR process defined by Bass et al. The first activity is the preparation activity. Here, the set of input files is selected, from which architecture information shall be reconstructed. Activity 2 concerns the domain viewpoint, and it captures domain information about a microservice architecture within domain models, and these domain models are expressed in a dedicated modeling language called the domain data modeling language. This activity corresponds to SAR phase 2 and 3 because it first transforms architecture information into models, and it is also possible by using our modeling languages to combine the reconstructed models by means of an import mechanism. Activity 3 is the service modeling activity. It targets the service viewpoint and it uses the service modeling language to reconstruct information about microservices, their interfaces, operations, and endpoints within service models. The service models can import domain models to show the relationship and responsibility of a microservice to a set of coherent domain concepts. Activity 4 is the operation modeling activity. It targets the operation viewpoint and it uses our operation modeling language to reconstruct information about microservice deployment and infrastructure nodes like service discoveries and API gateways within operation models. And to this end, the operation models import service models to show, for example, the deployment of previously reconstructed microservices. Activity 5 is technical refinement. Our modeling languages also integrate means that allow to assign technology information, for example, to microservices or operation nodes. And this information is to be reconstructed within Activity 5. Activity 6 is the post-processing activity. It corresponds to SAR phase 4, and it aims to answer hypotheses about the reconstructed architecture by means of the reconstruction models. In the following, I would like to briefly illustrate how the process works for the service viewpoint. So let us assume that we want to reconstruct a microservice architecture from its source code. And the source of the microservice architecture to be reconstructed is based on Java. So here you can see two Java listings. The first listing defines a class, and this class has the annotation at Spring Boot application, which means this Java class employs the Spring Boot framework to implement a Spring Boot application. And in microservice architecture, a Spring Boot application can conceptually be mapped to a microservice. In the second listing, a class is defined that has the at-rest controller annotation and the at-request mapping annotation. And it lies in the same package as the class defined in the first listing. So conceptually, the second class is an interface of the microservice that is implemented by the Spring Boot application shown in listing 1. The class in listing 2 also specifies an operation, also specifies a method, and this method conceptually maps to an operation of the microservice that is implemented by the Spring Boot application shown in listing 1. So if we show the conceptual mappings, the first listing is a microservice, the second listing is an interface for the microservice, at least conceptually. And this interface defines an operation that is here implemented as a Java method. And this operation has incoming parameters, has a fault parameter because it throws an exception, and also has an outgoing parameter because it returns some value. And this information is now used to reconstruct the information about the microservice architecture within a service model, because now we are in activity 3, service modeling activity, and the service model that is reconstructed is expressed within our service modeling language, and it makes this conceptual mapping that took place here visible. So in this third listing, you can see the service model that corresponds to the Java listings on the previous slide. This service model is expressed within our service modeling language and is one of the outcomes of activity 3, the service modeling reconstruction activity. So let's come to the validation. We validated our modeling method with Lakeside Mutual, which is a microservice case study architecture that can also be found on GitHub. And we also provide a validation package with the examined source code and particularly the derived reconstruction models that can also be found on GitHub. You can see the links here in the footnotes. In the following, I'm going to present the validation results per activity of our SAR modeling method. So on this slide, you can see a summary of activities 1 to 5. In the first activity, we selected the input file sets to reconstruct information about Lakeside Mutual from. And to this end, we selected the source code, build scripts, and configuration files related to the 4 backend microservices of Lakeside Mutual. We use the 4 backend microservices because they implement the business logic of the application, and we decided to rely on source code, build scripts, and configuration files because no extensive high-level architecture documentation for LM exists. So we executed our modeling method on 160 files in total with 8,858 lines of code. In activities 2 to 4, we reconstructed domain models, service models, and operation models from the input file set, each model kind expressed within one of our MSA modeling languages. and we created one model per model kind for each of the microservices. So we had 4 domain models, 4 service models, and 4 operation models. In activity 5, we also examined further technical configuration files that were not considered before, like for example application properties, files for Spring Boot, and a Docker Compose file that was contained in the top-level hierarchy of LM source code folder. And then we validated activity 6, the post-processing activity, in that we examined the reconstruction models for MSA-specific types of architectural technical debt, or short ATD, as they were defined by Toledo et al. In their paper. And in the following, I would like to present results for 2 of the ATD types. The paper contains the other ATD types and the results for them. So one ATD type in MSA is that there are too many point-to-point connections between microservices. We could see from our reconstruction operation models that Lakeside Mutual deploys an active MQ infrastructure node for asynchronous communication, but it is only used by one service. So it is highly likely that the other backend microservices of LM communicate via point-to-point connections. And probably this communication happens via REST because our service models show that the reconstructed microservices use REST as a synchronous communication type. Another ATD type in MSA is different middleware technologies for service communication. Lakeside Mutual uses one protocol and one technology per communication type. So there's one technology for synchronous communication and one technology for asynchronous communication. But this is quite common to MSA to use exactly one technology for synchronous and one for asynchronous communication. So this is not necessarily ATD type, or the risk for this ATD type is not necessarily high in Lakeside Mutual. However, we could also see from our service models that only 16 out of 26 REST operations were explicitly annotated with an HTTP method. This can lead to communication failures at runtime if a caller tries to invoke the other 10 REST operations that do not have an HTTP method. So the invocation can fail due to the lack of an HTTP method. So coming to the discussion, following the SAR process definition of Buzz et al., our modeling method currently has to be executed manually. Of course, this is error-prone, and in future works we plan to extend our modeling method with automation capabilities. The input artifact availability impacts the effort of our modeling method. So in the validation, we relied on source code to reconstruct the architecture of Lakeside Mutual, and it quite took some time. But the source code could also be replaced by, for example, concise database schema descriptions from which domain concepts could be reconstructed, or with API documentation for to reconstruct service interfaces from. So this could speed up the reconstruction process, because then then artifacts on a higher level of abstraction than source code can be used for the actual reconstruction process. The modeling method does, however, not constrain the input artifact types. So it does not prescribe to use source code for the reconstruction process. Our modeling method also supports technology modeling, but depending on the scope and goal of a SAR process, the technology-related reconstruction steps of our modeling method can safely be omitted as described in the paper. So if technology information is out of scope of a SAR process that uses our modeling method, you can simply omit the technology-related reconstruction steps. Coming to the future work. So in future works, we plan to extend our SAR modeling method with automation capabilities. We want to automate the derivation of reconstruction models via static source code analysis, and also automate the post-processing via static model analysis. We also plan to develop a code generator to support architecture refactoring starting from reconstruction models. So thank you for your attention, and I'm looking forward to your questions. And just let me jump over the references here so that you can also see them. Thanks a lot, and I'm looking forward to your questions.